Okay, so I think based on what I saw last week, that by the time we finished section, a lot of people were still a little bit confused about my three L'Hopital's rule problems. Is that true? Okay, so I was going to go over the L'Hopital's rule problems again quickly. So remember, I think the first one was fine, but the two that people seemed to have a lot of difficulty with were lim x goes to 0, x ln x, and lim x goes to infinity, x to the 1 over x. So can I get Fs in the chat if you were happy with these last time? Oh, okay, so great. How about Fs in the chat if you were miserable with these last time? Yeah, okay, that's more what I remembered. I remembered some people being pretty unhappy. So let me just review these quickly, because the techniques that you're going to need for these are very important, and they could show up on a quiz or a test. And I think that you'd be pretty hard pressed to come up with them if you hadn't seen them before. So, okay, so for the first one, remember we want to find some way to apply L'Hopital's rule, but we don't have the format of a L'Hopital's rule problem. Namely, we don't have some sort of fraction where it's f of x over g of x. So the only way that we can fix this, that I can see, is to do ln x over 1 over x, and then take a limit as x goes to 0. And so then you can just note that the denominator, well, it goes to plus or minus infinity, and the numerator goes to minus infinity. So then taking derivatives, you end up getting limit as x goes to 0, 1 over x over minus 1 over x squared. And then this becomes minus x, and you're taking a limit as x goes to 0. And so that, of course, just gives you 0. Okay? So for the second one, again, there's not really an immediate way that I see to apply L'Hopital's rule. So let's call this limit L, and then we'll say L is equal to, of course, lim x goes to infinity, x to the 1 over x, and then we can take log on both sides. So log L is equal to log lim x goes to infinity, x to the 1 over x. And then remember, I think in class you discussed the fact that you can take this from inside the function and put it outside. So lim x goes to infinity. And then you get log L is equal to 1 over x log x. And so now we just apply L'Hopital's rule again, and we get 1 over x divided by 1. And we're taking a limit as x goes to infinity. And so that just gives you 0. But of course, this is just log L, and we want L. So we exponentiate both sides, and we get L is equal to 1. Okay? Great. I hear silence, so I'll take that to mean that everyone understands this well. So for the next problem, if you want more practice with L'Hopital's rule, you can look on my worksheet, and I have 4 more standard examples of L'Hopital's rule problems on number 2. So you might want to go and try those out later if you're still shaky on L'Hopital's rule. Otherwise, you don't have to. Okay, so I want to start talking today. We've done a good amount about integration and limits. And so today I want to talk about integration instead of just taking derivatives. Okay, so first, I want to talk about U substitution. So when you're integrating, sometimes you'll get very lucky and you'll have some sort of function that is of this form that you're integrating. And you have to be on the lookout for this type of function where you might notice that the inner function actually has a derivative that's being multiplied by outside of the function f. So if you see something of this form, then the technique that you want to use is you can replace the function g of x by some variable u, and then you get f of u, and then because this is g prime, or derivative of g, you get du outside, and then u is a function of x, so it's really du dx, and then you multiply by dx, and you can cross these two out. And now you're just integrating, so this is in the case of an indefinite integral. And then if you have bounds that are a and b, then instead of integrating from a to b, in this case, you're going to be taking, what'll it be? So whatever you'd plug in for, so it would, I think, be u of a to u of b, okay? Does that make sense? Because you're, great, okay. So this is the basic idea behind u substitution. Let me give you a few examples to work on. First, cosine, yeah, thanks for the F's in the chat. X squared 2x. So this one is an easier example. Actually, all three of these are pretty straightforward, but you should still give them a try. And then the third one is, okay, so these are also on the worksheet in case you are having difficulty reading my handwriting, and I'll put you in your breakout rooms for a couple of minutes to work on them. So how many people do I have today? Cosine squared, cosine, oh, and I should be recording. Oh, there we go. Cosine x squared, cosine x squared times 2x. And so this is u, and this is du. And so then you're just integrating cosine of u, du, and that just gives you sine of u plus c. And then you just plug back in x squared. Okay? So for the second one, you have an integral 1 minus 1 over w cosine w minus ln w. And so you can note that the derivative of this thing is 1 minus 1 over w, and that's right here. So then we get another cosine u, where this is u, du, and this gives you sine of u plus c, and you plug back in what u is, and you get w sine of w minus ln w plus c. Okay. So then for the third one, you have the integral 1 minus x squared x dx. And so this time it's not quite as straightforward because the derivative of the inner function is minus 2x, right? And so then what you really have is root u times, so the derivative is minus 2x, and we just have an x. So then you have a minus root u over 2, and you're integrating that against u. And that gives you minus u to the 3 over 2, and then times 2/3, so that just gives you an over 3 plus c, and then you just plug back in u, and you get 1 minus x squared to the 3 over 2 divided by 3 plus c. Okay, so are people happy with these problems? Great, so people are still happy, good. So now that I've talked about some u substitution, I want to start talking about a more difficult integration trick, which is, oh, can I go back to number 2? Yeah, I can go back to number 2. It's right here. So now that I've, oh, the answer is sine w minus ln w plus c, unless I made a mistake. Okay. So, right, I want to talk now about trig substitution. And trig substitution, I think it's not quite the same as u substitution. And the difference is that with u substitution, you're trying to notice some sort of structure, which is f of g of x, g prime of x. So this is u sub. But with trig sub, you're not trying to notice a structure that's already there. You're just trying to find some variable that if you replaced x by this variable, then it would be much easier to integrate. So I guess one way to think about it is that when you're doing u sub, what you're really doing is you're taking a function x or g of x and you're collapsing it down to a single variable, okay? But with trig substitution, you're just taking a variable x and you're replacing it with a trig function, okay? So one is collapsing, one is really replacing. So let me also give you a few trig identities that are going to be extremely important whenever you're doing trig substitution. So probably you saw these in high school, and it's very important that you know them and can recognize when to use them. So the first big one is cosine is lowering powers. So if you have a function cosine squared of x, this is actually the same as 1 plus cosine 2 theta, or 2x divided by 2. And why might this be useful? So say that you're trying to integrate cosine squared x, okay? So I don't know how to do that. It's just, yeah, we know what the antiderivative of cosine is, but we don't know anything about cosine squared. But if we rewrite it as 1 plus cosine 2x over 2, then this is good because we can integrate this pretty easily. The first part just gives you that, and the second part gives you, so if you don't know this formula, you're in trouble because then you have no good way to approach this problem, or at least no way that I can see immediately. So the other one that's important is if cosine squared is given by this, we can find sine squared like by subtracting cosine squared from 1. And this gives you, so that's sine squared. So that gives you 1 minus 1 plus cosine 2x over 2. And that's just equal to 1 minus cosine 2x over 2. Okay, so you should know these two formulas, or at least one of them, and then you can derive the other one easily. So let me show you an example of trig substitution. I needed to give you the double angle formulas first, otherwise it wouldn't have made too much sense. So say that we want to integrate, and note that this is very similar to the last problem that I gave you. But the difference here is that last time I gave you an x outside. So when you had an x outside, you could just take the inner function to be u, and then you could take x to be du. But if I remove the x, then that's not an option for you. So instead, what you're going to want to do is you're going to want to replace x with cosine of x, okay? So, or let me say cosine of theta. And remember, if we're replacing x by cosine of theta, we know that x has to go from 0 to 1. And so if x is going from 0 to 1, let's see what this means for cosine of theta. Cosine of theta goes to from 0 to 1 when theta goes from minus pi over 2 to 0. So then we can integrate minus pi over 2 to 0. And now we just have to replace x with cosine theta in our equation. And we get 1 minus cosine squared theta. And then dx, so we're not just going to put in a d theta for x. We have to do d of cosine theta. And so this is going to give you 1 minus cosine squared theta. And then d cosine theta is minus sine theta. And again, we're going from minus pi over 2 to 0. And why did we want to do this in the first place? Well, because 1 minus cosine squared theta can be rewritten as sine squared theta. So then you get sine theta, or more precisely, I guess, absolute value of sine theta. And we're integrating, we have another sine theta. So then that gives you a sine squared theta, and you still have this minus sign out front. And you're going from pi over 2 to 0, okay? Great. So, okay, ignoring the absolute value for a second, we're going from pi over 2, we're going from 0 to pi over 2, or pi over 2, minus pi over 2 to 0. And what was our expression again? Our expression was 1, so our expression was minus sine theta d theta, okay? So is everyone with me so far? Could I get F's in the chat or a comment that you're not with me? Okay, I have one F and no other responses. Yeah, I can show the last page. These whiteboards aren't great because there's not a whole lot of space. Okay, so before I go further, let me just recap what I did, because this is kind of a confusing process. The idea is you have this integral that you don't know how to evaluate, but if x were replaced with cosine of theta, then you would know how to evaluate it potentially. So now we replace x with cosine theta, and we replace the derivative of x with the derivative of cosine theta. And that gives you a minus sine theta for the derivative, and you're replacing under the root, you're getting 1 minus cosine squared of theta. It doesn't matter, you can replace it with either and it'll still work in this case. Okay, so then once you've done that, you note that this is just sine squared theta, and sine squared theta square root gives you an absolute value. And you're going from pi over 2 to 0 here, okay? And you have a minus sign out front. So the next thing to notice is that if you're integrating from minus pi over 2 to 0, so that's, oh no, that's on this part of the unit circle. And so sine here is always negative because this represents sine. Oh, because the reason I didn't derive cosine squared is because I'm replacing x with cosine. And so here you have dx, not dx squared. So you just want to take the derivative with respect to cosine, which is our new x. So let's see. So, right, we're over here. So that means that sine is always negative, right? And so if sine is always negative, it means that absolute value of sine is just equal to negative sine on this region, okay? Because it's always negative. And so this is good news, because it means that you can just replace sine theta with negative sine theta. And we already had a negative sign out front, so that's gone. And then we get pi over 2 to 0 sine squared theta d theta. What do we do now? Well, I just suspiciously gave you the lowering power formula. So pi over 2 to 0, 1 minus cosine 2 theta over 2 d theta. You know how to integrate this. This just gives you theta over 2, and then antiderivative, that gives you minus sine 2 theta over 4. And then we go from pi over 2 to minus pi over 2, sorry about that, to 0. And that gives you, so you plug in a 0 here, you get a 0 here for the zeros, and then you're subtracting pi over 2. So you're subtracting negative pi over 2, so 2 minuses, and then minus, and then when you plug pi over 2 in into sine 2 theta, you end up with something of the form minus pi here. And so then the second term is just going to be 0 again. So then you get pi over 4. Okay? So if this is a little confusing, where did it divide by 2? Oh, we divided by 2 because when we did the lowering powers formula, we got a 2 in the denominator, right? We got rid of the negative. Yeah, these are good questions. We got rid of the negative sign because when we were integrating absolute value of sine theta, we noted that absolute value of sine theta, so this is always positive, and sine is always negative, right? When we're in this area. And so if sine is always negative and we want its absolute value, then all we have to do is multiply by -1. And so then we replace the absolute value here by minus sine theta. Okay? Great. So I guess trig sub is pretty hard. You guys covered it in class a little bit, right? Okay, but I guess people aren't happy with it yet. I think it's probably the hardest integration trick. So, okay, let me give you a couple of practice problems. I guess I'm a little bit apprehensive because I think that there may be hard if you haven't seen this before. So, but let me give them to you anyway, and you can try struggling with them a little bit. So 25x squared minus 4 over x dx. Yeah, just do this one for now, because the other ones are harder. So let me put you in your breakout rooms. All right, can I get some Fs in the chat if you are happy with that? Probably people won't be. Cool. Can I get F's in the chat if you had no idea what to do? Cool. So basically everyone. Yeah, okay. So I guess the best way to do this problem, so the problem isn't really the denominator, right? The problem is the numerator. You have this weird square root, and there's nothing outside that you can use as a derivative. So the intuition here is that you want to get rid of the square root again, okay? And so in this case, like, you know, it's a trig sub problem. So what you should do if you don't know what to do and everything else fails is you take the trig functions that you know and you start plugging them in and think about what might work, okay? So to expedite this process, I'm just going to tell you. The correct thing to put in, or one correct thing, because there are usually many, is you can put in secant of theta, okay? 2/5 secant of theta. So why would you want to put in the 2/5? The 2/5 is to get rid of this 25 and make both of the coefficients 4. Because if you have two coefficients and both coefficients are 4, then you're going to get a nice trig identity, right? Because you know that, or you should know that 1 plus tan squared theta is equal to secant theta. Okay. So that gives you, so let's plug this in. You get 4 secant squared theta minus 4 square root divided by 2/5 secant of theta. And now you also have to deal with the derivative here. So the derivative of secant of theta. What is the derivative of secant of theta? It's like, so it's 1 over cosine theta. And so maybe you want to use chain rule and you get like 1 over cosine squared theta. And then you get, it's chain rule, so you get sine times minus sine theta. And that just gives you, so like tan theta over cosine theta, right? Does that make sense? I just forgot the derivative of secant, so I re-derived it. Okay, so then you have your d theta here. Cool. So now this is very good because this becomes 2 tan theta, because, oh, okay, let me show some steps. This is 4 times secant squared theta minus 1, and secant squared is equal to 1 plus tan squared. So you get, oh, that should be an absolute value. So then you end up with 4 tan squared theta, and then you take a root and you end up with 2 absolute value tan theta. And then you have another tan theta over here. And then you had a secant theta in the denominator, but secant theta times cosine theta is equal to 1. So then you're just left with 2/5 in the denominator. And then you end up with 2 tan theta, or sorry, the 2's cancel. So you just get a 5 here, and you're integrating this d theta. Okay, so here you kind of are a bit stuck unless you actually have some bounds of integration, okay? Because if you don't have bounds of integration, this could be plus or minus, and so you don't really know what's going on. But so Does the process make sense to everyone of how you'd get to here? Cool. So I'm wondering if I should give it bounds of integration and go a little bit further. Maybe I won't right now, because in order to go further, if I give it bounds of integration, you're going to need a double angle formula for tan, which I don't want to introduce right now when we only have 5 minutes left. But so this is the idea. And once you put in bounds of integration, you're just going to have to put a plus or minus sign in front of the tan based on, you know, the scenario or where you are. Like if it's going to be minus on a domain, then you're just going to put a minus sign in front because you're taking the absolute value, and otherwise you'll just make it tan. So, okay, this was a very rapid and confusing introduction to trig functions and trig substitution. But if you didn't understand it this week, don't worry, you'll see it again, I think, in lecture. And next week, I'll have more problems for you on this as well. And if you are still, well, I think a lot of people are very unhappy. So I recommend that you go to the worksheet that I gave you and work through those examples. And also this video will be up on YouTube later today. So you can go to YouTube and watch this and go through the steps again slowly. And my office hours are also posted. I'm going to have office hours at noon today, noon until 1. So if you want to stop by and chat, feel free. It's the same Zoom link. All right, thanks for coming to section. You're the few, the brave. See you next week.